Professor Bialis here. In this video we're going to be talking about section 4.2, solving systems using substitution. In 4.1 we talked about how to graph two lines, see where they intersect, get the solution that way. The problem with that is graphing isn't the most efficient way of doing things, number one, and number two, if let's say you have a graph grid and the lines cross somewhere like that. There's no way of accurately getting that value. You can approximate it, but if we want to get an exact value, there's really no way of doing that without the assistance of technology. So what we're going to do is look at an algebraic method of doing this that will give us an exact value every single time. Okay? Now, before we jump into an example, there's one thing that we need to remember while we're going through these problems. When we're using substitution, we need to start by getting a variable by itself. Okay? So, start by getting a variable alone. Okay? Now notice I said a variable. I didn't say the x's, I didn't say the y's. Just get a variable by itself. Okay? So let's jump into an example, see what this looks like. So I'm just going to say solve using substitution. That's all we're going to be doing in this video. So we have this. Okay, now we have a system of equations. What we should notice first and foremost is we already have a variable by itself. We have that x equals in the second equation. Now, what that allows us to do, whenever we have two things that are equal, they have the same value. They may look different, but they have the same value. That's like a dollar bill and 4 quarters. They look different, but have the same value. So what that allows me to do is substitute one expression for the other. So wherever I see an x, it would be the same thing as me saying y plus 4. So what I'm going to do is take this expression and I'm going to substitute it in for the x in the other equation. Okay? Now one thing to keep in mind is when we do the substitution, we always want to use both equations when we do it. I see some students take this and they plug it right into the same thing. That's not going to work that way. Okay, we already know that these are equal. But if we take two separate expressions, we can kind of melt them in together. So what that brings us to is a new equation. The initial equation we were given was 2x plus 3y equals 13. But now instead of x, I want to say y plus 4. Okay? When we're given a linear equation, okay, we have two variables in it. We can't solve that and say x is 5 or y is negative 6. Okay, we have two unknowns. But when we have two equations with those two unknowns, we can pull them together into a new standalone solvable equation that has a single variable. Maybe longer, but it has a single variable. So let's now solve this. I'm going to start by distributing to get 2y plus 8 plus 3y equals 13. Combine like terms. Subtract the 8. And then divide by 5. And I can get y equals 1. Now remember though, that's not the full solution. A solution to a system has to have an x coordinate and a y coordinate. We got the y, now let's get the x. Now the good thing about substitution is whenever we have a variable alone, that equation is kind of set up to solve for that variable. So I can go right here, x equals y plus 4. Well, I can plug that 1 in for y now. X equals 1 plus 4, or x equals 5. And now I have my x coordinate, my y coordinate, and we're good to go. I could have also taken that 1 and plugged it into that top equation, but then I would have to do a little bit more algebra to solve for the x. So at this point I would just take the path of least resistance. Okay, always go for the easier path while you're solving. Now when you're checking, if you want to check these, I have to plug a 5 and a 1 into this, see that it works, and to this, see that it works. Okay, so that's substitution. Okay, let's look at a few more. For the rest of this video, I really suggest pausing it once I write a problem down and try it yourself. Okay, again, there's really nothing more that I have to show you with the actual process of substitution, so give it a shot. Okay, now when we're going through this again, the good thing about this one is we have a variable by itself already. So I can take this and put it in place of that y. That gives me a new equation. My initial equation was given as 4x minus y equals 2. But instead of y, I'm going to write 5x. So again, two things you got to look for. Number one, you got to make sure that you're using both of these equations. Number two, when you pull them together, your equation that you create needs to have only one variable. It can happen in a couple spots, but only one variable. Okay, now it's solvable. So 4 minus 5 is negative 1x, or just negative x, equals 2. I can then divide by negative 1, and there's your x. Now I can take that x value and plug it in here and solve for y, or plug it in here and solve for y. I'm going to go with this one simply because it's easier. No other reason besides that. Okay, so I've got y equals 5x turns into y equals 5 times negative 2, or y equals negative 10. And then pulling that together, I have x, comma, y, and there we go. Okay, let's look at a few more. Okay. Now, looking at this one, we have a little bit of an issue here because we don't have a variable by itself. However, we have the power to make that happen. So when we solve one of these equations, we are again going to try and solve for a variable, and namely the variable that is easiest to solve for. Okay, you can solve for this x, this y, this x, this y, but again, pick the one that's easiest. In this case, I'm going to go after this y here, because all that will entail is me subtracting the 3x over. So when I'm solving that, I'm going to subtract 3x, subtract 3x. So my new first equation is y equals negative 3x plus 5. It's the same equation, just rearranged. And now the second equation I'm going to bring down. And here is a new system. It's the same system, but it's written out a little differently. Okay, now I'm good to go with my substitution. So I'm going to take this expression here and plug it in for the y in the other equation. So what that gives me is 3x minus 2y equals negative 7. But instead of y, I'm going to say negative 3x plus 5. Okay? Now I solve. So I'm going to distribute a negative 2, be careful with the negative, and that gives me 3x plus 6x minus 10 equals negative 7. Combine like terms, add the 10, negative 7 plus 10 is 3, and then divide by 9. X is 1/3. Now, something I want you to realize, we're using substitution here, but all of these could be graphed, and then we get the answer off of that intersection point from the graph. However, would we want to be able to get that, or would we want to get that off the graph? I would try to avoid that. That's why when you dig deep into this idea of systems, graphing doesn't happen very often because there's so much gray area with a lot of the solutions. Here, it's 1/3. It's not going to be, well, maybe it's 2/5, maybe it's 1/2. We know exactly 1/3. Okay. Now we're going to take that x and plug in somewhere to get the y. Now I am going to suggest you go to the equation that had the variable by itself. That's because I plug it in here and I just have to calculate. I don't have to solve anything. Someone may tell you, well, the safest thing to do is always go to the original problem. Okay? If you made a mistake somewhere, then we got bigger problems. Okay? Then all of this is wrong. When we're checking at the very end, yes, you have to go to the original problem. But when we're still solving it, take the easiest part of the problem to use. Okay? Because again, while you're still going through the solving phase, if there's a mistake, then we have to go back and check for it later anyways. So I would just get to the end of the problem the easiest way you can. So I'm going to go with this. We've got y equals negative 3x plus 5. So y equals negative 3 times 1/3 plus 5. Those 3's cancel nicely. Negative 1 plus 5 is 4. So what I have is an x, comma, y, and there is your final answer. Okay, always be careful that you are writing the x first, then the y, because if I flip those, then it's a different point. Okay, so again, just to reiterate, if I'm checking at the very end, always the beginning problem. Okay, always go to that. But when we're solving, it's okay to use these intermediate equations to get that answer if it's going to be an easier way to do it. Okay, let's look at a few more. Okay. Now, a lot of people look at this problem and they start to freak out because, oh, there's a fraction in there. That's okay. Sometimes we just have to deal with the fraction. What we should be happy about is that we already have a variable by itself. So we don't have to do any work to make that happen. So I can jump right into the substitution and put this in place of that y. So what we get is the original equation is negative x plus 3y equals 6. And then I plug in the 1/3 x plus 2. As you can see, I used both of the equations to build that new one, and also I have a single variable there to look at. So what I get is a distribution, negative x plus x, because 3 times 1/3 is just 1. 3 times 2 is 6, and we're here. Next thing to do is combine like terms. These x's cancel out. So what we're left with is 6 equals 6. Okay? Now, when 6 equals 6, that's when we would say all real numbers in the past. However, that doesn't really apply to this scenario here. Okay? Remember, all real numbers is just, numerical answers, but we want ordered pair answers. So how do I write that? Think back to 4-1. That's when we had the set of all xy ordered pairs such that, and then you pick one of these equations, okay? I'm going to pick the top one here. Negative x plus 3y equals 6. And there is your answer, okay? Now I want to talk about this a little bit before we go on to the next example. Something like this is very easy to get incorrectly, okay? Where you make a mistake and then you get, an all real numbers, or I'm sorry, not an all real numbers, but this type of solution. So I would really suggest you take the time to check when you get that kind of an answer. Now, how do you check that? Okay, because there's nothing that you can just plug back in. So what I would do is think back to graphing. When this happened with graphing, what did we see? We saw the same exact line, so we had infinite number of solutions there. So if I wanted to check this, these equations should be the same equation. So I am going to take this right here, solve for y, and see if it matches this. Again, that's not a necessity, but it's a good practice to get into to make sure that this is the correct answer. If this is the answer, that means it should have been the same line. So I would add the x, and then divide by 3. And as you can see, these equations are exactly the same. Okay? So that verifies that this works. Okay? I would not suggest you do that every single time because that's a lot of unnecessary work if they're not the same. I would just go through the substitution, and then if you get this, then you can go back and check. Okay? So let's look at a couple more. How about this? Now, again, we look at it. We're using substitution, so we need a variable by itself. We don't have that. So we need to make a decision. There's no wrong answer here, but there is a better decision than others. To get a variable by itself, I would target this. Okay? So I am going to add a 3x to both sides. Now, I'm going to bring this top equation down. So this just copies down 5x minus 2y equals 6. But then the second equation turns into y equals 3x minus 3. Okay? Again, I chose that because all it took was one step. If I wanted to get this y by itself, I would have to subtract 5x, then divide by negative 2. Not only does that introduce fractions typically, but it will also require an extra step. So take the path of least resistance. Now, I have this system to solve. I am going to take this, plug it in for y, or substitute it in for y. Okay, so I got 5x minus 2y equals 6. And then I can plug in 3x minus 3. After that, it's just basic equation solving. Okay, I'm going to distribute a negative 2. I get negative x after I combine like terms. And then negative x equals 0. Since 0 doesn't have a sign on it, we've just got x equals 0. If we divided both sides by negative 1, we get that x equals 0. Okay? Now remember, here the x's canceled out. Here the constants canceled out. As long as the variable's still there, you're going to have a numerical answer to that. If the variables go away, that's when you get into this kind of a realm here. Okay? So x is 0. We still need to find y. I'm going to go back to this equation, the y equals equation, to get that. So y equals 3x minus 3. I'm then going to plug in. So y equals 3 times 0 minus 3, or y equals negative 3, because 0 minus 3 gives you that negative 3. And there you go. Okay? So let's look at one more. Okay, so there's a couple issues here. Number one, we don't have a variable by itself. Number two, there's not a single variable that clearly is easier than the others. They're all going to require the same amount of work to solve for them. So in this case, just pick one. Now, I am going to make a suggestion though, that you solve one of the equations for y. Okay, and I'll explain the reason for that in a second. Okay, so let's solve this top one for y. So I'm going to go off to the side. I'm going to have a 2x minus 3y equals 6. I'm going to subtract the 2x. And then divide everything by negative 3. And there we have it. Okay? So my new system is going to be y equals 2/3 x minus 2. And then I copy that second equation down. Okay, that now sets up the substitution. So we take this and plug it in for y. So what we get? Negative 4x plus 6y equals 5. And then I plug in 2/3 x minus 2. I distribute that 6. I get negative 4x plus, now here there's a few ways you can go about this, but I like 6 times 2 is 12. 12 divided by 3 is 4. And then negative 12 equals 5. These x's cancel each other out. And we get negative 12 equals 5. Now, we've seen this before. Whenever we have two numbers that are not in fact equal, we would say what? No solution. Not undefined. It's not that the system is undefined. The system has no solution. Okay, so make sure you use the correct terminology there. Now, again, in a situation like this, I would take time to check this. Okay. Now, how do we check it? What did this look like graphically? When there was no solution, we had two lines that were parallel. So, let's see if these lines are parallel. That means they have to be different lines, but they have to have the same slope. This is why I suggested in the beginning, if there's not a single variable that's easier to solve for than the others, solve for a y. Because now this first equation is in slope-intercept form. I don't then have to say, well, I solve for x, now I got to get in slope-intercept form to find the slope. It's already there. So what I'm going to do is solve this one for slope-intercept form. I'm going to go right here and use a different color. And we have negative 4x plus 6y equals 5. I would add this over. And then divide by 6. So y equals 2/3 x plus 5 over 6. Notice now, this and this are both in slope-intercept form. They're different lines, but they have the same slope. So that verifies the fact that we got no solution here. Okay? Again, that is just how you would check this type of a result. You don't have to do that every single time, but if you do have time, like at the end of an exam, those are the ones I would go back and check first, because they're the easiest ones to get an answer like this accidentally. Okay? So again, this is another way of solving systems. You can solve any system with graphing. The problem is it's not always accurate. So this gives us an alternative. Okay, we're going to talk about a third possibility in section 3 called the addition method. Okay, so in the meantime, work hard. Let me know if you have any questions, and I'll see you in the next video.